Okay, welcome colleagues. My name is Marcus Dekener. I'm the chair of the Load Research Chapter. Welcome today to a very interesting chat by Mike Barker. Let me just give you a brief introduction to Mike. I know he's well known to some of you, but we have attendees from several countries with us today, and I'll just give you a brief rundown of Mike Barker. Mike is a consulting engineer and a building services specialist with over 30 years experience in control and communication systems for the built environment. He holds a BSc Electrical Engineering from University of KwaZulu-Natal. Mike has worked on many of South Africa and East Africa's sustainable buildings, including Durban, Cape Town, UN Nairobi Convention Center, and head offices for Google and Microsoft in Ghana and Nairobi. He works with overseas organizations on extensive and ongoing research into design and operation of next-generation grid interactive buildings with their on-site microgrids. So that's IEEE 547, IEEE 2030, ISO 1780, 17800, etc., etc. So, ladies and gentlemen, that is Mike Barker. Mike, thank you so much for agreeing to present to us today. We are looking forward to seeing how we are going to move from potentially a situation where we have got generators and consumers to a situation where potentially everybody plays a role in the supply and demand on the network. Mike, it's over to you. Go ahead, please.
Yeah, thanks, Marcus, and thank you to the Load Research Council for the invitation. It's getting near the end of the year, and I think we've all attended many webinars. So this webinar is more about entertainment, maybe, than the heavy-duty technical details. So certainly we're not going to be talking about perhaps residential systems, in other words, single phase. We're going to talk about the bigger units, three-phase units, and it's not going to be a talk about what the inverter does for you and how inverters work, whether they're grid forming or otherwise. It's more about what the inverter can do for the grid, what your inverter can do for the grid. And we need to probably remember that in South Africa at the moment, our grid is a shining example of something that's working well. We don't want to damage it. We've seen what happens to our road networks. We've seen what happens to our rail networks. We have to put a lot of effort into understanding how we can work with our grid as good grid citizens. We don't want to damage or destroy it. So I've used this little slide often enough. We need to look to option number 3, where the grid and the renewables, distributed renewables, all work together. And that's exactly what I'm going to be wanting to do today. It's about how grid firming inverters can sing and dance with the grid and how we can make all of this play together. So one of the slides I've been putting up for the last probably 12, 15 years is something from Ernst & Young way back when they looked at the European market. And you'll see on the vertical axis, this is the cost per megawatt hour. And along the bottom is the time. And we don't really know what the time frame is. But what I always like to throw this out, you'll be able to see this and study it later, maybe if you download the presentation. But we all agree at some point we've reached, or we're about to reach, grid cost parity. In other words, if you look at the yellow line, where rooftop solar and local batteries, maybe called the microgrid, have the same cost of energy as the fully delivered cost of electricity from the grid. So at some point, we're going to reach tipping point number 1. People will argue we've reached it already. The other one that they throw in here, and remember this was 15 years ago, is that at some point in the near future, we're going to reach internal combustion engine and electric vehicle parity, both on cost and performance. When that will be, I don't know. My money's on around about 2030 in South Africa. China, they're way past that already. And then the interesting one, the dark horse, is tipping point number 3, because I'll leave you to go through this at your leisure, but it does suggest is that when the cost of transmission and distribution is equivalent to the cost of generating your own electrons on your roof and storing it in a battery in the basement, when you reach that point, there's no real reason for centralized generation anymore. And that raises all sorts of things that we need to think about. So at your leisure, you can go through this and think a little bit about it. The other one is, in South Africa, we talk a lot about small scale embedded generation. And the word small scale perhaps is it's not quite the right term. We can throw a lot of ideas around, but there's a school of thought, a growing school of thought. If you're a member of the IEEE, we've been discussing this for the last 15 years, but there's nothing small scale about embedded generation. If you look at DERs, distributed energy resources, and it's the old story, 1 or 2 of them are fine, but when you're looking at millions of them, millions of houses with 12 kilowatts on, those are big numbers, okay? And we're seeing this playing out in China. So this year was a important year for China, and we turned to them because they produce just about all the PV panels, all the inverters, and a lot of equipment that we are starting to use on a day-to-day basis in our power networks. If we look at the Chinese market, they've released a requirement for something they call a virtual power plant. So you might have heard of that before. The direct Chinese translation is an empty plan electricity factory. And that's exactly, in many, many words, what a virtual power plant is. So the Chinese government have said, listen, by 2030, we want 50 gigawatts of VPPs on the grid. And that's quite a large number when you look at the total. If you look at the square down the bottom, the left-hand side down here, if you can see the cursor, by 2030, according to one of the Chinese companies tracking, they reckon they should have 500 gigawatts of distributed energy resources. That's both residential and commercial and industrial. And the frightening thing is, with the 40 to 45 million electric vehicles, we're looking at about 2,000 gigawatt hours of storage. Now you bundle all of that together and you've actually got the basis for a massive virtual power plant. And we think it's going to dominate a lot of what's going to be happening in China. Now, why the interest in this? Well, the Chinese are going to be producing hybrid type inverters that are focused on virtual power plants, and these should be readily available. Remember, they only launched this year, but we know that a hell of a lot of research has gone into this. So by about 2030, you'll be able to go out and buy not only the hardware, but a lot of the software as well that you can run. So if you look at this little Chinese diagram here, this is the Chinese market. You know, South Africa is heading towards the SAIEE, the South African Wholesale Energy Market. Well, the Chinese are jumping onto that as well. This year, the Chinese released document 136, which focuses on that. And here we have the physical grid. So, you know, what they're talking about is the dual role between the load and the power plant, which is the prosumer. And Europe, they call it the prosumer. So very important to watch what the Chinese are doing, because they may well be dictating the direction we're going. And of course, virtual power plants are a big thing in America, Europe as well. Right, so about 2 months ago, our energy minister at a talk in Cape Town put up a slide looking at something called the comparison between grid forming and grid following technologies. I think he put it up to put, well, first of all, to suggest that South Africa is right up there with the latest trends, and also to put people's mind at ease, because we've just had that issue in Spain where the grid fell over. And there's a lot of concern that maybe renewables are not quite what we need in large volumes on our grid. So he put the slide up, and I have to agree with him. South Africa is right up there with the trends. If we have a look at this slide, there's a bunch of guys, the global power system transformation, and the key word is transformation. This particular consortium consists of CASO, just about every player, EPRI, everybody in the market, including the CSIR, including Eskom, and now the National Transmission guys. So they are part of this consortium looking at transformation. So that's certainly pretty good news, okay? And the question is, what is the transformation all about? And I'm going to suggest that we should be looking at something like IEEE 1547 as a guideline to the future, and how our inverters and our little small-scale embedded generation can play a part in supporting the grid, the one and only grid that we've got that works so well. So where do we go? Well, if we start looking at inverters, converters, we do have to understand that there's, first of all, there's no real definition at this stage of a grid-forming inverter, this wonderful magic grid-forming inverter. There is, however, a gray area between all these different types of converters, inverters, from grid following to grid supporting to grid leading, and then to grid forming. And it really depends to a large degree on what the manufacturers are doing with the software, the control loops, and the configuration of IGBTs, and increasingly so silicon carbide devices, and how they mix these together. So we're not going to dwell a lot on the types of inverters. We're going to ask ourselves, what exactly can these inverters do for the grid, and in particular for the feeder? So I'm looking more at distribution side, three-phase distribution, maybe the longer rural networks where there's bound to be issues. Okay, so quickly I need to discuss with you the IEEE Standards Association. So a lot of the standards that the IEEE put out are used day to day by just about everybody on this earth, all the way from Wi-Fi through to power electronic standards. A massive amount of work is put in. There's about 40,000 people working on standards. You're always welcome to take part. Anybody and everybody can jump in. I'm on a number of technical committees. And of course, there's a lot of corporate members playing a part. And at the moment, there's about, 1,800 standards, some of them at early stages. So why do we need standards? You can read it yourself. Clearly a consensus view. Most important, because we find ourselves talking to people across the world as common terminology, whether we're talking to the Chinese with their empty factory virtual power plant. We need a set of common terminology. For example, what is a grid forming inverter? Unless we have a common definition, we've got problems there. And of course, standards lead to frameworks, and from that, design rules emerge, making it a lot easier for us to deploy DERs and small-scale embedded generation. Okay, how does it work? Well, at the very top, we've got standards. They describe the mandatory requirements. Then the IEEE have a number of recommended practice documents, and that's seen as the preferred approach, the best practice. And then right towards the bottom is a set of guides where there is discussion on alternate approaches, and where there's no clear-cut recommendations, these guides spell out the various paths you can take to achieve the requirements. So that's the standard body. Right. So now let's get to the crux of it. We want to understand how our distributed energy resources, our DERs, can contribute and help out with the grid and what the interface looks like. So this is really the crux of it all here. a standard called 1547. It's been around since 2003, and before that even, the guys were working on that. And it really spells out two different paths to connecting your DER, your inverter, to the feeder to the grid. So first of all, the physical interface, which is the transfer of power backwards and forwards, and then a communications interface as well. Now, I'm not going to look at the communications interface. I don't think we're quite there yet, and I've only got a limited amount of time. Marcus is going to kick me off here. I'm already a couple of minutes into the talk. But what this standard 1547 does for us is it looks at reactive power and voltage control, pretty important on the grid. It looks at something new to many of us, is the response to abnormal conditions, which is a ride-through. Now, you'll remember that the Germans had an issue before when the grid frequency dropped. I forget what it was below some I think it was about 49.7 or 8 or something like that. All the inverters in the whole of Germany jumped off the grid, and that obviously leads to massive issues. So there's a lot of thinking put into this, and what you'd like your inverter to do is to actually ride through some of these issues. But again, we have to fully understand what the ride-through conditions are. So we'll touch on that briefly. Clearly, there's frequency support. Inverters can play a big part, and also active power control. And then a whole lot of other general interconnection and rating requirements, which is really the safety side of it, where you want your inverters to synchronize properly when they come back on. You don't want your inverters feeding into a dead grid and all those good things that we need. So if you looked at the 2018 version of 1547, there's 11 control functions, and you can set 60 parameters. So you can really fine-tune this particular standard and the way your inverter sings and dances with the grid using the different control functions and the 60 or so parameters that give you a lot of leeway. And all these parameters are adjustable. There's a couple of voltage regulation categories, 2 of them. And then the important ride-through, there's 3 different categories there as well. So if you had to ask me what 1547 is about, I'd show you the slide and say, great, guys, here it is. This is what it does. It's a hell of a long name to it. So, we just call it 1547 and get over and done with it. The other good thing, of course, is we spoke about good grid citizen, and 1547 goes out of its way to support that. A couple of, I won't go through all of this in detail, but certainly safety. We got somebody's mic on there. Right, so certainly safety is the first issue. We don't want to feed energy back into a dead grid. There's anti-islanding and a lot of good things that come out of that. Tripping and reclosure coordination, pretty important. In fact, you'll find that 1547 does a lot of good things and takes care of a lot of issues, perhaps some issues we haven't quite thought of just yet. Power quality is the big one on my mind at the moment, because we know a lot of certainly these cheap single-phase inverters and a lot of the other early inverters are pushing a lot of problems back onto the grid. If we want to, our inverters, if we ourselves want to be good grid citizens, we genuinely have to start thinking about what we can do for the grid. At the moment, we keep thinking, I guess, that, it's only one little inverter. What's it going to do for this massive grid? 100 kilowatts, the grid is 20, 30 gigawatts. But the point is, we soon are going to be approaching a world where there's going to be a massive amount of inverters, inverter-based resources, IBRs on the grid. And we need to start thinking what the combined and aggregated impact is going to be. So this is something we have to dig in deep. And if we want to maintain the good quality of electrical power, we've got to start looking at this as soon as possible. That's my message to you. Okay, so where did it all start? This probably gives you a better idea of these things. So back in 2023, 1547 came out, and to a large degree, at that stage, 1547 is exactly where our distribution system operating code is at this moment. I believe version 6.1 is the latest. I might be wrong on that, but 2019 timeframe. So the inverters shall not actively regulate voltage and shall trip at the slightest abnormal conditions. So that kind of makes sense. But we do know when you've got a lot of, when you have a inverter-rich feeder, you now need to start thinking differently. So in 2014, the amendment came out, and they started to say, well, the inverters may, not shall, may actively regulate voltage, may allow for ride-through, may allow for frequency response. And then in 2018, they started making these issues mandatory. And of course, we're waiting for the IEEE 1547 version 2025. It might be version 2026. And that particular version is going to start providing inertia. And of course, that's the big issue that people are wondering about, all the way from our energy minister down to I guess the man in the street, because he's heard about Spain and he's heard about all these other issues. And the first thing people look at is can power electronics, can renewables provide inertia? And nobody knows what that means, but this is the important thing to the man in the street. So the answer is 1547 probably is going to be able to do that in the next year or two, and it'll be mandatory. It's going to be required. So another way to look at it is 1547 is not just one standard. It's a number of standards, starting with 1547.1, which is a set of test procedures you use for conformance, all the way through to the UL guys jumped in with a certification approach. So you can actually go out and buy 1547 compliant devices, whether from China, a lot of them from America, of course, and some from Europe. They are widely available. If you dig into the specs, you might find reference to UL 1741 as well. That's the certification. Right. So when I started looking at this way back in 2015, round about there, the question was, what are power electronics based generation going to be doing to the grid? And the guys were working way back then. So in July 2018, they released TR68, looking at the impact of inverter-based generation on the grid and short-circuit performance. And then more recently in 2020, they released the TR67, looking at the impact of 1547 itself on smart inverters. So the word smart inverters, to many of us, implies that the inverter complies with 1547. Marketing guys, anything can be smart these days. But if we talk about smart inverters, we should be thinking an inverter that has intelligence and that can play nicely with the grid. So looking at the requirements that came out of this and the impact, number one, voltage control, reactive support is needed, frequency response and control, and then short circuit levels, how to take care of that. And then, of course, right at the bottom, the planning process. So to the LRC, to you guys, you got to start planning for this as well. And how do you incorporate inverter-rich feeder into your planning? So about July, this slide was put up by one of the speakers at the Load Research Chapter's webinar, and looking at the work they'd done, they also identified, in this case, overvoltage as probably the greatest threat. And I think we see that as well. So I want to briefly discuss 1547 in terms of overvoltage. I mean, it covers 1547 covers a good deal of ground. I don't have the time. You don't have the time to go through it. All of it in one session. So let's just jump into the overvoltage issue and have a look at at what 1547 can do from that point of view. So the mandatory issues are protection and tripping. When exactly do you trip your inverter? And there's a number of approaches laid out. Voltage ride-through is actually not tripping, but it's at least giving the grid a chance to perhaps recover before you start dumping millions and millions of inverters. And then, of course, in terms of overvoltage, we have the voltage regulation capabilities, which is, you can think of it more as preventative actions that can be taken. So the first one, the mandatory one, is the volt VAR. You're pushing in not real power, but you're trying to now control the voltage on the feeder. And then as the last option, you start to look at the volt watt or the volt power side of it. You don't really want to go down that road because nobody wants you to start curtailing the power that they're pushing back into the grid. People are pretty sensitive about that. So first of all, you start with your reactive power and see if you can't correct the grid. And then next up is you start curtailing. And if you think of it this way, this approach of 1547 is treating the source of the problem. Now we hear a lot of discussion about how you can resolve these issues by putting in extra devices on the feeder, even from some sort of clever advanced tap changer on the transformers to rotating machines to provide inertia. 1547 says that's fine, but let's have a look at the source. Let's have a look at each individual inverter. And again, how can they be good grid citizens and work together to protect the feeder, to protect the grid? Okay, so then there's a number of categories. So this voltage ride-through is a very interesting topic, and we can spend a lot of time on it. But one of the first things you've got to realize is all of this is adjustable. All those parameters that we spoke about earlier, you can play around and set up your voltage ride-through requirements to suit. Typically, let's just jump to category 2. You can see anything up to 1.1 per unit, fine. That's great. And anything down to 0.88 PU. That area is great. You can operate there. Then looking at the bottom, we've got the time, and you can see depending on how long these issues last, these dictate how your approach to it, whether you trip, whether you ride through, all of this being adjustable. And this is all detailed in a lot of documents. People keep asking me, do they have to pay for 1547? The answer is yes, it's the IEEE spec. So you've got an ethical requirement to pay for it if you want it. However, there is a bucket load of documents available for free on the internet rather. Of course, all of it downloadable from places like NREL and EPRI, of course, and the transformation group that I spoke to you about. And if necessary, I can release a list. We'll put it in a folder. We'll chuck a whole lot of the better documents into a folder, and that'll give you some feel for it. Now, 1547, of course, is not just one standard. It's a range of standards, starting off with 1547 itself, working its way through many different requirements that we find on the grid, including application guides. That's dot 2, dot 3, cybersecurity, dot 4, microgrids, along with IEEE 2030 dot 7 and 8. A lot of good direction provided by these standards for islanded systems or microgrids. And then the one I'm going to talk briefly about, of course, is probably the one closer to your heart as well, is a guide for energy storage system interconnection. And this is not at transmission level, this is at distribution level. So 1547 is a comprehensive set of standards going all the way back to 2003. And there's a lot of development, and all these standards are being revised as well on an annual basis. So yeah, let's have a look at dot 9. Okay, interconnection of energy storage, or a BESS. The focus here, again, define the terminology as state of charge. What does it mean? Operational capacity. Clearly, if your inverter has a battery behind it, you can start playing a very important part in terms of volt var support, volt power. You've got the battery there, and it's always there, unlike solar or wind, which might not be there on the day. Over in the UK, they're doing a lot of fast frequency response as well, and maybe we're going to be needing that. The South African wholesale energy market does talk about the ability to buy this sort of resource and pay for it. And of course, we've got our ride-through exemptions that play a part when you've got battery-backed DERs. And safety, another big issue. And then the one that's close to my heart, because I believe this is the biggest issue, is going to be vehicle to grid. And this is where all those millions and millions of vehicles, remember, China at the moment has got something like 40 million electric vehicles. And where South Africa will be in 2030, I don't know. But if the Americans aren't buying Chinese EVs, and Chinese EVs are very profitable, far more profitable than an ICE vehicle, the Chinese are going to be pushing a lot of these electric vehicles into Africa. They're pushing them into Brazil, Mexico, the Far East, even Australia. I think we're going to see a lot more electric vehicles in. And it doesn't take many electric vehicles with this, let's say, 40 to 50 kilowatt hour batteries to play a massive and important part. So how these the bidirectional energy flow between EVs and the grid, how that plays a part is something that we've got to start thinking carefully about. And again, 1547 talks to that. And I think this is an issue we need to start addressing in the new year. Okay, so many of you are going to be saying, well, we don't really like the IEEE for various reasons. They're not an international standard and not an IEC standard. And so the answer there is there's many other ways to skin this cat. So the Chinese, again, have got the NB/T standards, not quite as advanced as 1547. The Germans have got a set of standards as well, and all of these are good standards. Basically, if you went out and bought an inverter, a good quality inverter on the market today, and you read through the spec, you'll find that these inverters comply with just about all these standards. And of course, the IEC standards, none of them really do what 1547 do. But if you bundle a whole lot of them together, you start getting you start getting the same sort of results. And the reason why I mention this is because in South Africa, we just love to write our own standards. We're a very small part of the market. But I'm pretty sure somebody's going to sit down and put together a South African SAN standard and duplicate what 1547 does. Let's hope they just take it and rename it and not fiddle too much. And of course, 1547 is very adaptable. Remember, when it comes to something like 1547, you basically have to set it up for each and every feeder, which, all of them are pretty different. All right, so we did say we'd talk about grid forming technologies, okay? And the transition guys, they've got a special interest group, a council, they call it, looking at these technologies, at grid forming itself and how grid forming can play a part. And whilst there's no actual definition at this stage, I think this slide does give you a pretty good idea of where we're at the moment. We've got a lot of rotating mass on our grid, holding things together, handling any abnormal situations, and a small amount of inverters, okay? But that in the near future is going to change dramatically. We're going to see possibly almost all of the generation, not the power, but the energy coming from inverter-based resources. In other words, distributed energy resources, and very little rotating mass. So, what does that grid look like? What does the future grid look like? This has to be addressed. The current definition The suggested definition is simply what I'm showing you here. And that's the GFM as a voltage source. And it's going to do a lot of good things for the grid, we hope. So if you read between the lines, you'll see that they are looking at it doing what 1547 does. In many cases, there's a IEEE standard, the 28,000 standard, which looks at how grid forming inverters connect to transmission side of it. In other words, it's another important set of standards, and 1547 is starting to borrow a good deal from the IEEE 28,000 standard. So it's going to be interesting to see where we go in the next 5 years. But believe me, a lot of people working on it, including a couple of South Africans, and this is always pretty good news. Okay, so we nearly done there. Oh, the last thing is, many years ago, maybe even 10 years ago, I put out a document trying to make the case for 1547 and the IEEE family. If you read this last point here, municipalities and its citizens benefit from timely adoption of rigorous, clear, up-to-date standards for safe and reliable interconnection, integration, and parallel operation of DERs. Okay, so this is something that's still very, very relevant. And the document I put out then looked at a couple of things, including the future. And I borrowed a lot of this from guys overseas. And the last point they made, and I agree, the possible and eventual adoption of 1547 or similar, and of course the other IEEE family standards, requires early local evaluation, timeous and widespread promotion, and continuous education of all stakeholders. And we shouldn't underestimate the work needed to do that. It's not clear to me that any of our municipal engineers have any idea of perhaps what 1547 is about. I've tried to talk to many of them, and not much interest. Now, I might be wrong. I'm hoping I'm wrong. I'm just hoping that, they didn't want to talk to me in the first place, or they felt that, I was wasting their time. But there's a lot that needs to be done to get our feeders ready for the future. So with that, I'm going to hand back to Marcus, and I've got it down to about 40 minutes. Great. Thanks, Marcus. Over to you.
Mike, thanks very much. This is quite a mouthful, and we may need updates on this into the future, but thank you very much for efforts. And it is much that this first view is very useful to many, I'm sure. Okay, if we can go to the questions, folks, please feel free to drop your questions into the chat box if you want. Otherwise, raise your hand, and you're welcome to field your question yourself. I have a question here from Michael Schmidt. Hi, Mike. As per pre-SA grid code, all category B and C systems must operate in power factor correction mode. Category A systems are not required to do so, i.e. may operate in PF equals 1 mode. Would it not be sensible to specify that all category A3 systems must be operated with the inverter set to power factor correction mode? Mike, that's quite a mouthful. You care to comment?
Yeah, so certainly, again, 1547 does look at power factor. I'm just trying to pull it up here as I speak to you, and I might not find it in time. So under the reactive power and voltage control, they do make allowance for constant power factor control mode. And you would then set a configurable power factor set point. So it does tackle that as one of the modes, along with volt var and watt var. You do have a power factor control mode. I hope that answers the question.
Thank you, Mike. Michael, are you happy with that answer?
Yeah, it's just at the moment the city took the approach of, well, it's not specified in the NRS 097 that it needs to be in power factor correction mode. So that's what we're doing. But my opinion is that we should rather have everything that's bigger than 350 kilowatts actually operating in that mode. I think on the assumption that that would assist grid stability. Am I right or am I wrong?
Yeah, so I think that is the starting point. I think the best thing we could do is if you can get hold of Marcus or myself, let's take this discussion further. There's a lot to be said about that. What we do find, and again, I'm talking not because I'm an expert, but because I know a lot of the experts, is that there's interaction and often unintended consequences of these various modes, whether it's volt-var or watt-var. But sure, the power factor has to be there as a starting point.
Okay, so in other words, I could tell my superiors, as of day X, I recommend that we state on our permission to install letters for the category A3 systems that the PV inverters need to be set in power factor correction mode instead of power factor equals 1 mode.
I'm not going to comment on that. I don't fully understand this. That's why I'm asking you if we can discuss this further.
Yeah, gladly.
Which city is this? This
Cape
is the
Town.
first. Is this Cape Town?
Yeah.
So Cape Town have got some pretty concrete ideas on where they want to go. I think we need to dig into this. Yeah, I think let's hold that off.
Yeah, and I'll pull Ishmael into the Ishmael and Naeem into the conversation then. Okay, thank you.
Thanks.
Thanks, Michael. Mike from Corin, we have a question. How important is it to start being more strict about what kind of inverters are used with residential solar PV installations?
Yeah, that's a political question. Clearly, we only have this one grid, and the more inverters, the more RBRs, inverter-based resources that we start putting onto any feeders are going to cause problems. We've already heard, and all of these are anecdotal stories, we've already heard that a lot of inverters are tripping and people don't quite know why they trip all the time. And I'm pretty sure it's about the power quality. So I think the starting point would be much like power factors, the starting point. I think power quality is a starting point. So how do we make sure that the inverters are of the right quality? That's going to be a difficult one. Everybody will assure you there are UL standards, and the 1547, by the way, has a pretty good set of standards for power quality. I might even be able to just call that up quickly while we talk. You know, it does start, in my opinion, with these issues as put up here. Your inverters to be good grid citizens, safety, power quality, okay? Those certainly are the issues. So a UL certified inverter is probably a good place to start, I would think. Corin, any thoughts?
That's fine. Thanks, Mike. Gives me a better idea. It's just at the moment, people are usually just connecting their solar PV without the idea of pushing back into the grid, but that will come. So that was just my question, how strict should we be? Thank you.
Yeah, 1547 does allow you to prevent any backflow. And we know backflow causes many, many issues. IEEE are doing quite a bit of work on backflow through distribution transformers, the reduction in life of the distribution transformers when you have large amounts of backflow. There is a lot of thinking that suggests that we want to keep all the energy on the feeder and not have that much backflow. I mean, I spoke about the advanced tap changing. If we don't want backflow through distribution transformers, then there is a new animal called the energy positive neighborhood. Now, for my sins, I'm part of a group of guys that they're called the BIPSA, the International Building Performance Simulation Association. And I'm also working with Annex 96 crumbs. There's so many numbers. So Annex 96 are looking at grid interactive buildings, and in other words, how the smart load works with the grid. And the energy positive district or energy positive neighborhood is all about keeping energy within the neighborhood rather than trying to push it all back into the grid. Clearly, we do have issues where people or a virtual power plant might well want to sell and wheel energy back through the grid. So in other words, an aggregated set of buildings, and the South African wholesale energy market, SAIEE certainly does support that. Wheeling is clearly the big thing at the moment. And, if you wheel out of an urban district, that does mean you're putting a lot of focus on the performance of these distribution transformers, to my understanding, are step down. They've never been designed to work the other way. They can work the other way, but that's when they deteriorate. They run these harmonics and many other issues I'm not going to go into at the moment, mostly because I'm still learning, starting to learn about these issues. So, Marcus, over to you. Thank you.
Thank you, Mike. We've got a question from Chart van der Walt here. Eskom will be decommissioning a lot of coal-fired generation soon. Could the old generators be repurposed to run as synchronous by adding flywheels? Question mark.
Yeah, so that's interesting. Now, if you're an institute member, the Large Machines Group had a chap on from Spain, when was it, 2-3 weeks ago? And he spoke about exactly that. Firstly, he didn't seem to think you needed a flywheel. You can get a lot out of just spinning up one of these units. There are specialist devices you can buy. I think what we need to do, Marcus, is just get hold of that recording and make that available. He went into it in great. Professor Johan de Kock, I think, and a couple of other guys were there as well, asking many questions about this particular issue.
Thanks, Mike. That's great. Yes, let's certainly do that. Etienne Dupree makes a point. Just a note, IEEE does not take preference over grid code in South Africa. The required control modes are mentioned in the grid code.
Is that the distribution grid or the transmission grid? But I do agree, at the moment, IEEE has no standing at all, and it's perhaps something that the regulators need to start looking at. Not necessarily IEEE, but the requirements.
Yeah, certainly. There is an issue of kind of grid sovereignty and making sure that what we have is what we want. Would you agree, Mike?
Yeah, no, okay. Certainly. Yeah, so I mean, a lot of work has to happen. I think IEEE 28000 as well can certainly provide a lot of good guidance and points for discussion for anybody looking at the grid code, and likewise for the distribution code as well.
Yeah, thank you. That's great. Folks, any more questions? If you have a question, we've got 79 people on board. Please feel free to either type your question in the box, or you can put hand up and ask verbally. You're most welcome. Either mode is fine. Mike, I've got a comment about the communications. If the communications with the standard, the demands seem to be quite high, what are the issues that you see may come from this?
Marcus, communications, you mean between inverters?
Between area electric power system and the resource.
All right, so I deliberately haven't gone into that. There's a lot of discussion. I mean, at the moment, you understand one of the communication protocols is actually Modbus. And then I think there's two others as well. If you're looking at virtual power plants, like I discussed, the ones that they're planning to roll out in China, then you certainly do need to communicate with the inverters. Is that where you're going with this?
Yes, certainly. Obviously, the issue is the ease of aggregation and similar techniques.
Yeah. So, look, I think as a closing remark, I've been fortunate enough to get the team driving 1547, the latest version of it, and many other resources experts from EPRI, from CASO, that's the Californian grid people, and we can get them, and I think it would be best if we get them to start presenting on this, especially to our regulators and to the guys from ESCOM and the guys from the Munichs. If we can round up everybody and get the 1547 guys to start discussing where these standards are going, I think that would help a lot of people. Remember, what I tried to do today was throw together a brief introduction. In addition, I think there's a lot of value to getting a couple of the guys from China. So the good thing about the IEEE, which has 480,000 members around the world, was a lot of the English-speaking Chinese engineers are members of the IEEE. A lot of the standards we're talking about, 1547, 2030, etc., have been put together by Chinese engineers. And clearly, they're the guys who are going to dictate what inverters do. And we need to start roping them in to come and talk to us. You'll understand that the IRP 2025 that was released, there was a document as well from the Chinese power utilities, and they commented it. They had a look at it, and their comments are there to download and read. So the Chinese are well aware of where South Africa is trying to go, and we need to hear from them as well with SAWEM, with the wholesale energy market, the VPPs. There's a lot I think we can learn from the Chinese. Language has always been a barrier. That's why I don't think we know so much about what they're doing. But they are the 800-pound gorilla in the zoo, and they're going to dictate where the world goes with a lot of this. I mean, they already tell us what panels, we just buy their panels. We'd have no say over anything to do with panels. And likewise, soon inverters, batteries, etc. Thank you.
Thanks, Mike. Folks, we have time for one last question or comment. Anything from the audience, you're most welcome. Just a quick poll from the audience. You can give a reaction. Is there appetite for more presentations similarly to unpack various parts of 1547 to the South African industry? Hands up or thumbs up from the audience if you want. Okay. Thanks, folks. Mike, it looks like there's no further questions that I'm seeing from the audience. From Load Research Chapter point of view, and to our colleagues in SAIEE and all those others attending, we'd like to thank you very much for your effort in opening the book on 1547 for us. And also, it's quite good to learn that there are municipalities and others making entry on this in South Africa, and we look forward to hearing more in future. Mike, thank you very much for your presentation, and I will bid you farewell.
Good, thanks. And thank you to everybody for attending, and to the Load Research Chapter for the invite. Thank you then.
Thank you, Mike. Everybody that's in the audience, we invite you to make contact with the Load Research Chapter, and hopefully we will see you again in the future.